In this series of videos, we're going to be discussing the concept of polarity, which is important to understanding why water can dissolve certain substances and not other substances. In order to understand what polarity is, we need to look in detail at the sharing of electrons that occurs in different types of bonds, starting with the simplest bonds, the covalent bond in hydrogen gas. If we remember that a bond is just a pair of electrons that are shared, we can look in more detail about how those electrons are shared, which is based on electronegativity. Remember that electronegativity is a measurement of how strongly an element is able to attract electrons. So hydrogen's electronegativity, if we look on the periodic table, is approximately 2.2. which means that this other hydrogen also has an electronegativity of 2.2. Now, this might seem like a silly question, but I'm going to ask it anyway. Which element wants the electrons in its bond more than the other one? Hydrogen or hydrogen? If you answered hydrogen, congratulations, you are absolutely right. Another way of phrasing this is that neither hydrogen wants the electrons more than the other one. So if this dotted line represents exactly halfway in between the two hydrogens, that would mean that the two electrons within hydrogen's bond would be exactly on the line like this, showing that these electrons are shared completely equally. This phenomenon is what we call a nonpolar covalent bond, which we can abbreviate as NPC. Now, we remember that electrons have negative charge. Now, if the electrons are exactly halfway in between the two hydrogens, does either hydrogen have more electrons than the other one? Well, that answer would obviously be no. So we could say, instead of this, that each hydrogen has an equal amount of negative charge because these electrons are shared completely equally. Now, if we take a look at the polar opposite situation, see what I did there, we can look at an ionic compound, and again, we know because NaCl is an ionic compound, it doesn't have a sharing of electrons at all, because in an ionic bond, electrons are fully transferred from one end or from one element to the other. So what would this look like? Well, if we were to draw sodium and chlorine, we know that chlorine only wants to gain one electron and sodium wants to lose its one electron. And so that's exactly what happens. Sodium's electron goes over here to chlorine, and chlorine gains a full negative charge, and sodium gains a full positive charge, like so. And that the bond that forms is not due to the sharing of electrons, but due to the attraction of a negative charge to a positive charge like this. Now, if we, again, represent this as how far away the electrons are to the dotted line, we see that sodium's electron goes all the way over here, whereas chlorine is viewed as pulling sodium's electron all the way over here. And for this reason, chlorine has a full negative charge, while sodium has a full positive charge. This is the exact opposite situation as with hydrogen, where an electron is fully moved over to one side. But as we'll see with the covalent bonds below, they're not quite so cut and dry as our extreme examples here. For example, if we take the bond between hydrogen and nitrogen, if you check your periodic table, again, hydrogen's electronegativity is 2.2 and nitrogen's is about 3. Now, if we measure the difference in electronegativity between these two, this comes to 0.8. This number is less than 1.7, which is the number that's required to make an ionic bond, but it's not 0 either, which means the electrons are not transferred, but they cannot be shared equally the way that hydrogens are. If we look at this visually, Remember that nitrogen and hydrogen form a covalent bond. Their difference in electronegativity is not big enough for a full transfer, but where would the electrons be? Well, if nitrogen wants the electrons significantly more than hydrogen, maybe the electrons would probably be here instead, showing that the electrons have moved closer to nitrogen and farther away from hydrogen. Again, this isn't enough to say that nitrogen has fully gained an electron, but we can see, because of nitrogen's higher electronegativity, that these electrons are closer to nitrogen than they are to hydrogen. This phenomenon here is what we call a polar covalent bond, in which the electrons are shared, because again, not enough difference in electronegativity for a full transfer, but here we can see that the electrons are much closer to nitrogen than they are to hydrogen, so we say that they are shared unequally. Now, because of this, because these electrons, again, like all electrons, have negative charge, and because they are closer to nitrogen, that means that nitrogen has more negative charge than hydrogen does, because these electrons are closer. But unlike sodium chloride, which has a full transfer, this cannot be a full negative charge. So instead, we represent this like this. This symbol is the lowercase Greek letter delta, which represents that there is a partial charge. We'll talk more about this later. Next, if we consider the bond between hydrogen and oxygen the same way, again, here's the dotted line that represents exactly halfway in between the two atoms, and we know from the periodic table that oxygen's electronegativity is 3.4 and hydrogen's is 2.2. So just like with nitrogen, oxygen wants the electrons in its bond more than hydrogen, and even more than nitrogen. Therefore, we would expect the electrons in its bond not only to be closer to oxygen, but even closer to oxygen than they would be in a hydrogen to nitrogen bond, again, showing that oxygen is better at attracting electrons than hydrogen is. So therefore, because these electrons are closer to oxygen and farther away from hydrogen, oxygen is also going to have this partial negative charge, because it is gaining electrons, but not strongly enough to be a full ionic bond. Now, what about hydrogen? What's going on with hydrogen? If nitrogen and oxygen are pulling the electrons away from hydrogen, we can say that both nitrogen and oxygen are gaining electrons, even if it's not enough to be an ionic bond. But that must mean, because the electrons are moving away from hydrogen, that hydrogen must be losing electrons. And as we know from sodium up here, if you lose electrons, you are going to have a positive charge. But just like with nitrogen and oxygen, because this isn't a full transfer, this positive charge is not a full positive charge, but instead is a partial positive charge. What we have just discovered here is the existence of something called dipoles. Again, di meaning two, obviously, and you can think of pole as being the same word that you use in terms of a magnet. We know that magnets have a north pole and a south pole, but the actual way to describe poles of magnets is a positive pole and a negative pole. Now, because this is a covalent bond, because the electrons are not transferred, we use this Greek letter delta to represent that there are partial positive and negative charges that occur because the electrons in the bonds are unequally shared. Now, I alluded to this when we took a look at the difference in electronegativity. The strength of the dipole, meaning how much negative charge is in the partial negative pole, or how much positive charge is in the partial positive pole, this number is based on the difference in electronegativity. For example, if we go up here, we see that the difference in electronegativity between nitrogen and hydrogen is 0.8, but the difference in electronegativity between oxygen and hydrogen, 3.4 minus 2.2, is 1.2. What this means is that the electrons in the bond are going to get closer to oxygen than they are to nitrogen, and because oxygen effectively has these electrons closer to it than nitrogen does, its negative dipole is going to be stronger than nitrogen's is. So if we want to compare three polar covalent bonds or with three dipoles, again, we can compare nitrogen and hydrogen, oxygen and hydrogen, and an intermediate one, chlorine and hydrogen. We can do the delta En calculations, 3.4 minus 2.2, with hydrogen and nitrogen, as we saw, is 0.8, and oxygen and hydrogen, 3.4 minus 2.2, is, as we saw before, 1.2. And if you check your periodic table, chlorine's electronegativity will come to 3.2. 3.2 minus 2.2 is exactly 1. So what this means is that the bigger the difference in electronegativity is, the closer the electrons in the bond are going to move to the more electronegative atom, and therefore the stronger its negative dipole is going to be. So what that means is that because hydrogen and oxygen has the highest difference in electronegativity, this negative dipole is going to be stronger than hydrogen to chlorine, and hydrogen to chlorine's negative dipole is going to be stronger than nitrogen to hydrogen's. In the next video in this series, we're going to take a look at how we can use the difference in electronegativity and understanding the difference between polar and nonpolar covalent bonds in order to look at whether an entire molecule has a dipole or not.